Hi, I want to talk about an application of Faraday's law that applies with any circuit, anytime there's any loop of current. A current is going to generate a magnetic field. If that current changes, that magnetic field is going to change, and that magnetic field is always going to exist through some loop. So all circuits are always going to have some self-induced EMF. And that self-induced EMF leads to a new material electrical component property that we call inductance. So if we look at Faraday's law says the EMF that we see induced is equal to the number of loops that we have times the change in magnetic flux per loop. Well, the magnetic flux is something that's being created by the system itself. There's some current going through the system. That current creates a magnetic field through the area of that loop. So for a situation where we have a uniform magnetic field, like a toroid or a solenoid, then that magnetic flux would just be directly proportional to the current. So the changing magnetic flux would be some physical parameters times our changing current. So what we could do is pull that factor out and take a look at the flux that we have per coil divided by the current causing that flux. And we'd be left with our changing current with respect to time. And self-induced EMF is directly proportional to the changing current with respect to time. And that constant of proportionality is what we call the inductance. So for a toroid or a solenoid, the inductance would be the number of loops that we're dealing with times the magnetic flux per loop divided by the current that's creating that magnetic flux. And the unit that we have to measure inductance is called the Henry. And 1 Henry of inductance is equal to 1 volt-second per amp. So let's take a closer look at a solenoid. For this particular solenoid, it happens to be 0.8 meters long, and there are 1,600 loops of wire making up that solenoid. And each one of those loops has a diameter of 2 meters, so the radius would be 1 meter. Now for a solenoid, the magnetic field inside a solenoid is equal to the permeability of free space, mu naught, times the number of turns per length, times the current that's going through that solenoid. So to find the flux, that would be a uniform magnetic field times the area over which we have that magnetic field, which is just the area of the coil. Our flux would just be our magnetic field times our area. So mu naught times the number of turns per length times the current times our area, pi times the radius squared. So to find my inductance, I'd take my flux, divide out the current, so that goes away, and then multiply by the number of coils, n. So for a solenoid, we get an inductance that's equal to mu naught times the number of turns squared divided by the length of the solenoid times pi times the radius of the coils squared. So for our solenoid, the permeability of free space is always 4 pi times 10 to the minus 7 Tesla meters per amp. N is 1,600. We square it. We divide by 0.80 meters, multiply by pi, and 1 meter squared, and that gives us a total inductance of 13 henries for that solenoid. Thanks for watching.